Okay, one more frequentist confidence interval, and then we'll move on to Bayes. As was the case with the Rubin causal model, I'm going to give the Bayesian short shrift for the reason I've already mentioned before. Most people in our department do statistical inference this way, and so that's the way we're going to, rightly or wrongly, that's the way we're going to do it. I'm working now with a new variable. We're going to do several of these in class. V sub I stands for vote choice, harking back to earlier videos when this was introduced. So we scored 0 for those who supported Obama, or let's say voted for him, and 1 for those who voted for Mitt Romney. One more time, we'll assume we're targeting Ole Miss students. We'll make all kinds of assumptions that all 13,000 of them voted. All 10 of ours did every time we sample. We get 10 more who claim to have voted for either Obama or Mitt Romney. Of course, these are nonsense data. I just made them up. And we're working with a binary dichotomous variable, singling this thing out on purpose. They're really neat. When you sum, you use the same estimator to find the central tendency, the mean. You add them all up and you divide by the total. And that formula is the estimator. And our estimate we call p hat instead of x bar, because p hat has really neat and special properties. One is that the variance term simplifies all the way to this. There's almost nothing here. Notice that. We have n, p, and 1 minus p. So these things are easy to do, and I want to show you. I want to show you one, and then make reference again, as we did earlier, to what happens when the sample size explodes, to the confidence interval. But let's build the one we have on hand right now. So the mean on this variable vi is 0.5, put it in here. 1 minus p, 1 minus 0.5. That's a difficult calculation, 0.5. See how easy these are? This is going to be then the square root of 10. Well, let's do this first. 0.5 times 0.5 is 0.25, and then we're going to take the square root of that, right? To find the standard error. I'll put them over here. Square root of that, 0.5 times 0.5 is 0.25. The square root of 0.25, of course, is 0.5. So the numerator there is going to be 0.5. And square root of n equal 10, I think we already saw, is 3.16. And now let's build a confidence interval where we do two standard deviations. This thing here, 0.5 divided by 3.16 is going to be about 0.16. Now we're going to do 2 standard deviations, so twice that is going to be about 0.32, right? So let's put the interval up. The interval is nice and bounded on 0 and 1. Remember, the early quick primer talk on probability, by law, they cannot go below 0 and they cannot go over 1. Our estimate of p hat is here, 0.5, and we're going to subtract twice the standard error estimate, which is 0.16. So we're going to subtract 0.32, which should give us 0.18, right? Yes. And then over here, we're going to add 0.32, which should give us 0.88. Oh, 0.32. Excuse me, 0.82. Did I do this wrong? I criticize students all the time for the inability to do arithmetic, simple arithmetic, in their head. This, in fact, is correct. So I got it right. Look at the damn interval. Excuse the language. Our sample is so small, we're learning nothing about the population proportion. We want to know p. We want to know p from the 13,000, or p from the millions and millions of voters, if our target population is American voters more generally. We want to know, to be able to say something about the population, something about it, indirectly. We want to be able to say something about it. And this is completely worthless, but we can again do a more realistic scenario rather than choosing an n of 10. I'm going to erase these. Let's just go straight to 1,000. That'll be nice because this is going to turn. We're just going to move these things around, right? So 0.016 and doubled is to 0.032. So 1,000, then we're going to go over here. 0.532, and we're going to take 0.032. So this is This is 0.468. Now we're saying, once we've moved from sample size from 100 to 1,000, now we're saying that the next 100 times that we go to the pot and draw a sample of size 1,000, we're going to expect 95 times out of 100 to get a result between 0.468 and 0.532. When you see in a journalistic description of a public opinion poll, and you read the term poll has a margin of error of plus or minus 3%, this is pretty much what they're talking about. This is not pretty much, it generally is in fact what they're talking about. A couple of standard errors, exactly 1.96 standard errors, but a couple of standard errors on either side of the point estimate of the sample proportion. To find standard errors on different kinds of variables involves different kinds of calculations, and is correctly or incorrectly becomes standard in the journalism in journalism norms to report what would be essentially the confidence interval around a proportion estimate. That's pretty good. That's pretty good. So do I know anything about what the real proportion from the 13,000 would give me? My Bayesians would remind us that this entire thing is artificial, and that the frequentist idea is to work over long-run frequencies and repeated sampling. So long-run frequencies, finding frequencies distributions on that variable, and we get the p hat of 0.5, and across repeated samples over and over and over again that don't really occur. So those samples don't really occur, and we can't then say we're 95% confident that p falls in here. We're just 95% confident that we will continue to get p hat estimates that fall in here going forward. So as you go to the Bayes, so we're going to do some of these in class together. Play with this good luck because it's easy and simple, and you can visualize things. You'll discover that the standard error doesn't just shrink or get large because of the square root of n, but that actually what's up here matters too. 0.5 times 0.5 is 0.25. That turns out to be the maximum value that could possibly be in the numerator. And what it tells you is that the 50th percentile, which is a really important point when people study democratic processes in politics, the 50th percentile is the most difficult to estimate. So these would be wider here than they would be if we went over there. That's actually sufficiently interesting to do a problem together on in class. That's the intro to the frequentist idea of making an inference from sample to population. I filled in even the lingo of estimation, estimator, estimate, and we're going to generalize it to relationships between two variables, and then ultimately relationships between more than two variables, where we find statistics that are not any longer sample means or simple proportions, but that represent that sort of first jump through the causal inference hoop, the establishment that two things are not independent, using sample data and making inferences from the sample data to the population. What a strange move this is going to be from video to video, because Bayesian school of thought is completely different. And it begins with the idea is that the Bayesians actually will tell you where they think the population value, if they believe a population even exists, they'll tell you with a quantifiable number how likely it is that they believe it resides in an interval. Bayesian statistics, as we'll see, eschews the idea of objectivity. Here we're pushing the concept of probability onto the things that we're studying, onto simple relative frequencies, and assuming the probability derives from there. And the Bayesian, as we'll see, rejects that notion and instead embraces the idea that probability is subjective.